feedback block HS, and this feedback, basically the role of this feedback is that so that you can modify the actual output and by comparing it with the reference input. Okay, so now, so this is the same system. So now the closed loop, so if the system is an open loop one, so in case of an, if the system is open loop, that means that the HS, the value of HS is equals to 0. So that means HS is not there connected. So the system simply reduces to, you have RS as your input, GS as your forward transfer function, and then output is CS, right? So that means you can write that the closed open loop transfer function GS will be equals to output CS by input RS, right? So now similarly we'll try to see what is the closed loop transfer function. So in case of in case of this closed loop transfer function, so we'll start from the basics. So first we'll write the, so BS will be equals to CS multiplied by HS. Okay, then ES is equals to R minus B. Then you have C will be equals to E times ES multiplied by GS. Now what you will do is that we'll just substitute these substitute these above equations, and we'll find out what is the value of the CS by RS. Okay, so here you substitute just, so you have GS, RS minus BS, you substitute BS with this CS into HS. So that means you get here. So if you take this one, so CS multiplied by 1 plus GSHS will be equals to GS into RS. So from here you can write that CS by RS, that is output by input, will be equals to GS by 1 plus GSHS. So this is the basic closed loop transfer function of a basic of a very simple closed loop system. Okay, so you see that in case of an open loop system, the transfer function was only GS, but the moment you have a feedback element involved, that means there is a feedback sensor, so that means then the output or the overall transfer function becomes GS by 1 plus GSHS. So that means the value of the overall transfer function that actually gets modified, and the modified by the feedback, the effect of the feedback element comes into play, and the overall transfer function of the closed loop system that is changed. Okay, so now we'll see why do we need this kind of a feedback. Like, if I don't have a feedback, then the system is much easier to analyze and the transfer function is much more easier. So why do we need a feedback system? So mainly the advantages that of any feedback provides is that, first of all, if you have an open loop system, then there is no control over the output or how the output is changing with respect to different disturbances or noise or those things. Those are not in the control. So you are unable to control any kind of interference which is happening to the output or any kind of modification which is happening to the output signal because of unintended signals like the disturbance, noise and all. So because if we use feedback, then what we can do is that the control variable, it actually follows the reference value very accurately. Secondly, what we can do is that by using feedback, we can nullify or we can reduce the effects of external disturbances that can have external disturbances on the control variable. Similarly, if there is any kind of variation in the system, like variation in the system means suppose you have the controller or the process parameter, there is some changes in the process parameter, like you have the forward path transfer function, we saw that it was GS. So now let us say that if there is some variation in the value of GS. So if there is no feedback, so then if the value of GS changes to something else, so that means my output will also change. So for the same reference input, the output that we are getting will be different. But if we have a closed loop system, if we have a feedback, then the feedback is there to help you reduce the effect of these kind of variations which might come or in a system, in the controller, in the other process parameters. So the effect of these kind of variations, they can be reduced to a large extent by using a feedback. Similarly, the feedback in the control loop, it actually improves the speed of the response, and so this we'll see later on. So this might look like just a statement now, but we'll discuss later on that how the speed of the response is actually increasing, or it is because we are using the feedback characteristic, because we are using the feedback elements. So is it like the feedback is always good and it does not have any disadvantages? No. So obviously everything will have its own advantage as well as disadvantage. So the disadvantage of feedback is that obviously the system complexity increases. So now you have multiple more elements which are present in the system. So previously, in case of an open loop system, you had only one, let's say you only had the plant. So you only had to control the parameters of the plant. But now in case of when we are using a feedback, so you need a feedback sensor. So you need to modify or you need to control or have a look at the feedback element also. So that means the overall system complexity that becomes greater when you have a feedback. So this is one disadvantage you can say. Also the forward path gain also is because in the previous case you saw that if there is an open loop transfer function, then open loop transfer function is GS, but the closed loop transfer function, it gets reduced. So it is GS by 1 plus GS into HS. So it is reduced by a factor of 1 plus GS HS. So that means that if in a closed loop system, if you want a specific output, so that means the forward path of suppose there is some specific value of this GS. So in case of a closed loop system, obviously the value of GS is less. So if you want to keep the same value of GS for the closed loop system also, so that means what you need to do is that the forward path gain should be much higher. Okay, and also there are some possibility of system instability because of the feedback there can be certain like oscillations in the output which are in some cases which are like not desirable. Okay, so now we'll see so whatever we have told right till now, so we'll see how we can verify these things. Okay, so first we'll see that how a feedback system, using a feedback in a control system, will help you in reduction of parameter variation. Okay, so reduction of parameter variation means because what the feedback will do here is that it will reduce the sensitivity of the system to parameter variations. So what we mean by parameter variation is that, so if you have a simple open loop system, so this was my open loop system, so you have GS, output is CS, input is RS. Okay, so in case of a simple open loop system, CS will be equals to GS into RS. Okay, so now let's say because of some reason the value of GS changes. Okay, so now GS becomes equals to GS plus delta GS. So the moment the value of GS changes, so that means the output will also change. So output will change means, let's say the output now becomes if this is like C dash S, so that will be equals to GS plus delta GS multiplied by RS. Okay, so this is nothing but GSRS plus delta GSRS. So GSRS was the open loop output CS. Then you have another, so let's say this is delta CS. So delta CS will be equals to delta GS into RS. The change in output because of certain parameter variation of, because there is a variation in the forward transfer function by a value of delta GS is given by delta CS is equals to delta GS by RS. Okay. So now let's see that what would happen if the system was not open loop, rather it was a closed loop system. Okay, so let's take the previous example. So the closed loop system has a feedback element of HS. Okay, so that means now the output will be, so we have seen that for the closed loop system with a feedback of HS, so CS by RS is equals to GS by 1 plus GS HS. So from here you can write CS will be equals to GS into RS divided by 1 plus GS HS. Fine. So now for the previous case, let's say now again this value of GS, it changes to GS plus delta GS. So that means again this C is also changing. So let's say that is C double dashed. So C double dashed S will be equals to, so you will have GS will be now replaced by GS plus delta GS whole thing by R into RS divided by 1 plus okay. So now there is this assumption that the change in parameter of this GS, that is a very small change. Okay, so that delta GS is much less than G of S. So the magnitude of the variation in the forward gain or the forward transfer function, that is much less compared to the original value. Okay, so now if this is the assumption, then we can write this equation to be equals to so in the denominator, what we can do is that we can just neglect this delta GS into HS, this part, and we can write as this. So if you just simplify again, so this will be GS into RS divided by 1 plus GS HS, which is nothing but the previous value of CS, plus you have delta GS into RS divided by 1 plus GS HS. Okay, so that means from here, so this is C and this is delta C. So if you write, so delta CS in this case is equals to delta GS into RS divided by 1 plus GS HS. So now here you see that because of using the feedback, so previously if there was no feedback, if it was an open loop system, then for the same amount of variation in the value of GS, the output variation was delta GS into RS. But now here you see, if you are using a feedback system, a negative feedback mechanism, and you are making the system as a closed loop system, then the change in the variation in the output that we are getting because of the change in GS, that is delta GS, that has been reduced by a factor of 1 plus GS HS. Okay, so that means that by using this feedback, the output variation due to the system parameter changes is much less as compared to the case when the system was an open loop system. So this is like one you can say that this is one of the advantages of using a feedback. Okay, similarly, there is because of if you are using a feedback, then the feedback has its effect on the sensitivity of the system also. So sensitivity means the sensitivity of the overall gain of the negative feedback closed loop control. So if that transfer function or the overall transfer function is given by t, so if the sensitivity of this overall transfer function t or the overall gain t to the variation of the open loop gain g, that is defined as the ratio of the percentage of change in t to the percentage change in g. So the sensitivity of a system, that is basically defined as the percentage change in t divided by the percentage change in g. Okay, so t is basically the closed loop gain, overall gain of the closed loop system, and g is the gain of the forward path only. That is, the open loop gain is given by g and the closed loop gain is given by t. So the variation of the closed loop gain due to the variation in g, that is known as the sensitivity. So you can write the definition of sensitivity. If you have like a very small variation, so for very small incremental changes in g, so you can write the sensitivity S of t. So t comes as the superscript. So change in t due to variation in g, so g comes in as the subscript. So st of g will be equals to nothing but the fractional change in the or the percentage change in the overall gain divided by the percentage change in the open loop gain. So that means delta t by t divided by delta g by g. Okay, so this also you can write because that write as a delta of ln of t divided by delta of ln g. Okay, so you can write st of g will be equals to g by t multiplied by delta t by delta g. Okay, so this is the sensitivity of the overall sensitivity of the overall transfer function or the overall gain due to variation in the open loop gain. Okay, so let's say now let's take the example. So you have an open loop system. So that means in an open loop system, in an open loop system basically t will be equals to g because there is no, so the overall gain will be equals to the open loop gain only. So then you can write st of g will be equals to delta t by delta g into g by t. So that means this will be equals to 1. Okay. So this is the case when there is an open loop system. So now let's say that let us consider the closed loop case. So in case of closed loop system, so the value of t will be given by g by 1 plus gh. So actually here I am not writing g of s because, and it's sort of like understood that we are talking about in the frequency domain. So everything is associated is a function of s. Okay, so we are just for the sake of simplicity we are writing on only the new this g and h this, and we are not like g will be obviously gs, but we are representing it as g only. Okay, so now you have if there is this closed loop system with the feedback element h, so then t, the overall transfer function or the overall gain will be given by g by 1 plus gh. Okay, so now if I want to see that what is the value of, similarly I want to find out what is the sensitivity of st of g. So we can say that st of g here will be equals to, similarly we'll have to do the partial derivative of this with respect to g and then multiply it with g by t. Okay, so g by t is, okay, so if you do this del t by del g, can you tell me what the equation will be? Can you just quickly do the calculation for delta t by delta g and then tell me what is the value of st of g?
Ma'am, 1 plus GH.
Sorry?
1 plus GH.
This will be equals to 1 plus GH. Are you sure?
No, ma'am, no, ma'am. Sorry.
Then what is it?
Ma'am, we'll get H. Only H.
What is this value of delta T by delta G?
Ma'am, it's G by T, ma'am.
Sorry?
G by T.
G by T.
Yes, ma'am.
So what is G by T?
1, ma'am.
Why is G by T 1? Because now the value of T is not equals to G. The value of T is equals to G only if the system is an open loop system. When you have a closed loop system, then the transfer function is given by T is equals to G plus G by 1 plus GH. Isn't it? For an open loop system, the value of, so when you have an open loop system, so this is your overall transfer function. But when you have a closed loop system, then your overall transfer function is something else. So you have an H over here, this thing comes over here. So the overall transfer function changes. So in this case, in case of a closed loop system, the overall transfer function T will not be equals to G. Right, it will be equals to G plus G by 1 plus GH. So now you have T equals to G by 1 plus GH. Right, so now you find the value of delta T by del G. You tell me what this, you tell me just what del T by del G will be. Am I writing the equation right? Is this correct? So this you just have to do the differentiation, right? So here, since we are dealing with the partial derivative, so that means we are assuming that only G is varying. So obviously, so you have G by 1 plus GH. So this is in a fraction form. So that the derivative of this function will be the denominator whole square, and in the numerator you will have this denominator term multiplied by the differentiation of the numerator, which is nothing but 1, because del G by del G is equals to 1, and then minus you will have the numerator G multiplied by the differentiation of the denominator, which is equals to H, right?
Yes, ma'am.
Okay, so if this is the case, so then now you can write ST of G will be equals to, so del T by del G multiplied by G by T. So now you just substitute 1 plus GH whole square, and you have G over here, you have G by 1 plus GH. So G and G gets cancelled out. 1 plus GH goes to the numerator. So this and 1, this gets cancelled out, and you get 1 by 1 plus GH. So this is not only 1 plus GH, this is 1 by 1 plus GH. Okay, so now if you compare this the value of this is for the closed loop system, right? So for the open loop system, the value of STG was equals to 1, right? And for the closed loop, the value of STG is equals to 1 by 1 plus GH. So that means you see that this value is obviously lesser than 1, right? So that means that if you have a feedback mechanism, then the sensitivity of the closed loop system with respect to any variation in the value of G, that is getting reduced by a factor of 1 plus GH. So that means that the sensitivity is much less. So that means even if because of some reason there is any parameter change, so that means my output will not vary much if there is a feedback mechanism included in the system. Whereas if there is no feedback, if the system is an open loop one, then the effect of that variation in the output, that will have a much more severe effect on the output of the system. Okay. Similarly, if you want to see the, okay, so now you can see something else also. So this was the parameter variation with respect to if there was any variation in G. Okay, so this calculation is for variation in the value of G. So if there is any variation in the value of G, how the sensitivity of my system is getting affected in case of open loop system and in case of a closed loop system. Now we can see that there can be some variation in the feedback element also. So now let us say that in H, there are like two parameters G and H. So if you want to find the feedback, the sensitivity of the overall transfer function with respect to the feedback sensor, so we will denote it as the sensitivity of the overall transfer function T with respect to H. So that will be given by delta T by delta H multiplied by H by T. Correct? So similarly again, the value of T is equals to G by 1 plus GH. So from here again you do the partial derivative and you will get minus G by 1 plus GH whole square into, so you have G into G and you have H by G by 1 plus GH. Okay, so this is equals to minus GH divided by 1 plus GH. Okay, so now if the value of GH is very high, so let's say GH is large. If GH is very large, then what we can do is that we can ignore the term 1 and you can say that the sensitivity STH will be equals to minus 1. So that means if there is any change in the value of H, that gets directly reflected in the output, because this is ST of H is equals to minus 1. So that's why this is very important that we need to make sure that the feedback sensors, they are not affected by any kind of environmental changes. We need to make sure that there are no variations in the feedback, like as much as possible. There are like no variation in the feedback sensor. If there is any variation in the forward gain, that can be taken care of by using the feedback mechanism. But if there is any change in the feedback sensor itself because of any kind of environmental changes, then that has a severe effect on the output. So we have to make sure that the feedback sensor is not affected significantly, you can say. Is not affected by any kind of environmental changes significantly, because if there is any change in the feedback element, that will get directly affected, that will directly affect the output of my system. Okay, so till now do you have any doubts? So now we'll see what is the sensitivity of the overall transfer function with respect to any kind of a particular parameter variation. So in general, a system sensitivity with any particular parameter with a transfer function is expressed as, so it can be expressed in this polynomial form. So Ts, you can write Ts is equals to n of n, which is a function of h and alpha, and by denominator d, which is a function of s and alpha. So now if you want to find the variation in t, sensitivity of t due to variation in alpha, so then you have to write St of alpha will be equals to delta of ln n by ln delta ln alpha at alpha 0, where alpha 0 is basically the nominal value of the parameter around which any kind of variation is occurring. So the overall sensitivity of the overall transfer function with respect for any kind of variation in parameter alpha can be written as Sn of alpha minus Sd of alpha. Okay, so now if you have a very highly accurate open loop system, then the components of GS, they must be selected such that they meet the specifications very rigidly, because there is no control over the output, because it's an open loop system. So that means the value of GS has to be fixed and it should not be affected by any kind of external parameters in order to fulfill the overall goal or overall output that we are trying to measure. But in case if you are using a closed loop system, then this rigidity of selection of the value of GS, that becomes little bit relaxed. So in case of an closed loop system, the value of GS is very less rigidly specified, you can say, because any effect that might be there on any effect of any kind of parameter variation which can be there in any of the forward transfer function or anything, that can be basically taken care of by the feedback mechanism. Okay, so in overall, so the improvement in the sensitivity, there is obviously when you are using a closed loop system, there is an improvement in sensitivity. So that means the output is becoming less sensitive to any kind of unintended variations in the system. But obviously the moment you are using a closed loop system, so there is a trade-off. So the trade-off means trade-off comes from the point of loss in the system gain. So if you have an open loop system, then the gain of the system is only G, but the moment you have a closed loop system, the gain, it gets reduced, and it gets reduced by a factor of 1 plus G into H. So that means the improvement in sensitivity, that is basically that results in a loss of the overall system gain. So this, you can say, this is like one of the disadvantages of using a feedback mechanism. So now, for example, so now we'll see that, let's say that we have a feedback amplifier and we have a negative feedback that is applied. So let's say in this figure, so you have a system which has the input or the transfer function of the system is A, and there is basically a potential divider is present. So the output of the system is E0 and the input is EI. And because of the potential divider, whatever is coming here, that is the modified output which is coming here for comparison with the reference input, will be equals to K into E0. Okay, so now let's assume that the input impedance is infinite and the output impedance is 0. So a very ideal system. So then you can write the transfer function of this system. So if you draw the block diagram, you have your input as EI, then you have a comparison because of for this, then the forward path gain which is given by A, and the output is E0. And from E0 through this feedback mechanism, this feedback potential divider, so that is coming here. So and the value of this feedback is given by K, which is nothing but the ratio of R2 by the overall R1. Okay, so now from this equation you can, so this is like, you can say that this is, as of now we have seen that the forward loop is basically G and the feedback path is given by H. So you can write the overall transfer function of this system. So E0 by EI will be equals to, if that is given by T, so that will be equals to A by 1 plus Ka. Okay. So now if you want to find out what is the sensitivity of this overall transfer function with respect to any variation in the forward path gain, that is A. So that will be dt by dA into, or rather it would be delta t by delta A into A by T. So that will come as 1 by 1 plus Ka. So now if the values of A and K, like they are given, if the value of A is 10 to the power 4 and K is 0.1, then you can say that the sensitivity of the overall transfer function or the overall gain with respect to any variations in the forward gain, that is equals to 0.001. So that means that initial is, so as compared to the, so the value of t is equals to 10 as compared to the value of the forward gain, which was 10 to the power 4. Similarly, you can find out the sensitivity of the overall transfer function with respect to the feedback sensor also, and the feedback sensor also it will give you a value of -1, which we had already derived. Okay, so for, you can say that if the value of A is very large, if the forward gain is very large, so what you can do is that you can ignore the value of ignore 1. So that means the output or the overall transfer function becomes equal to 1 by K. So that means for a very large forward gain, you can say that the overall transfer function is independent of the forward gain and it depends only on the value of the feedback sensor. Now comes there is another application for, or positive or advantage of using a feedback. So this is basically it has the control over the system dynamics by using feedback. So the moment you have a so let's say that now you have a system which is given by this block diagram. So K dashed by S plus alpha, this is your forward path transfer function, and it has a unity feedback. So that means the value of H is equals to 1. Since the value of H is equals to 1, so that is why the block H is not shown and it is just like sort of shorted, you can say. So now you can write that CS by RS will be equals to, if it is an open loop system, then CS by RS will be nothing but K dashed by S plus alpha. Okay, so if that is the case, so then this K dashed, or you can just substitute this and write it in a different form, K by tau S plus 1, where you can say that K is equals to K dashed by alpha and the value of tau is equals to 1 by alpha. So this is the open loop case. Okay. So now if you have, and we have already seen that in case of a transfer function, if the roots of the denominator that is known, that will give you the position of the poles, and the roots of the numerator that will give you the position of the zeros of a system. Okay, so if your system is K dashed by S plus alpha, so that means the poles of the system will be given by, if you make S plus alpha is equals to 0, so that will give the pole location for this system. So that means the pole of the system will be at S equals to minus alpha, and tau is defined as the time constant, so that is given by tau. And if you want to see the DC gain of the system, so DC gain of the system means gain at 0 frequency. So gain at 0 frequency means you have to substitute the value of S by 0. So that means it will be equal to K. So that means the DC gain of the open loop system will be equals to K. So now in the second case, let us consider that we are using a unity feedback system. Okay, so the moment there is a unity feedback, the closed loop transfer function, it changes, and it changes to something like K by 1. If you do the calculation, you will see that the change is K by 1 plus K divided by tau CS plus 1. Okay, so here what is happening is that the value of tau C is given by tau by 1 plus K. So now now this is your overall, the closed loop transfer function is given by this one. So if you want to find the pole location, so you can see that the pole will be at S equals to minus alpha plus K dashed. So that means when we were dealing with an open loop system, the pole was placed at minus alpha, but the moment there is a closed loop system, the pole position shifts and it changes position to minus alpha plus k dash. Okay, and also the initial time constant for the open loop system was tau, and for the closed loop system the time constant gets reduced and it reduces by a factor of 1 plus k. Also similarly the DC gain also initial for the open loop system it was k, and for the closed loop system it is k by 1 plus k. So the DC gain also reduces. So these are like the three conditions which are this is how the pole position changes, time constant gets reduced and the DC gain also gets reduced. Okay, so the implication, okay, so we will talk about the implication of this change in pole position and time constant on the system dynamics or the response time in the next class, because I think it's already time and you might be having another class after this. So is there any doubt till now?
No, ma'am.
Okay, so fine. So tomorrow is a holiday. So we'll have our next class on Thursday and we'll continue our discussion on this one. And probably I'm hoping that by tomorrow, by the next class, I would be able to finish this first module of the syllabus. And we will be having a quiz after I finish the first module. That probably I'll announce in the next class when we will be having a quiz. Okay, so in case if you don't have any doubts, then we can end the class now. Or if you have any doubts, you can ask me.
Thank you, ma'am.
Okay, thank you.